So another application, we again have two cars start moving from the same point. They tell us what time the car leaves. First car started traveling north at 10 a.m. at a rate of 60 miles per hour. Second car started traveling east at 11 a.m. at a rate of 75 miles per hour. And they want to know how long it will take for the cars to be 600 miles apart. So this one's slightly different than one of our previous examples. What we're trying to understand is we actually are looking for time when they say how long it will take for the cars to be 600 miles apart. So again, I'll go with a diagram to give me my gears in my brain moving. If you're starting off from the same point, remember one car is traveling north at 10 a.m. and the other car is traveling east. That's to the right at 11 a.m. And at some point in time, they want to take a picture exactly where the cars end up being 600 miles apart. So this also leads me to understand that, we've got ourselves a right triangle. That means that Pythagorean theorem is probably going to come back and help us with setting up the equation and solving this problem. So that's really good news. I like the Pythagorean theorem. So the trick is this. Again, you're trying to figure out, what's the length of each of the legs in order for us to set up our equation. Well, we could say, we do know we have an idea, the a squared plus b squared at this point, one's a, one's b, is going to equal 600 miles squared, or just say 600 squared. So we at least have kind of an idea of how we want to approach this. But we need to come up with some sort of numbers or expression for a and b. So this is done by understanding, again, how long has each car been on the road? So I'm going to start off again with the first car. At this point, the first car starts at 10 a.m. And I'll compare this. The second car. I'm going to go underneath a little bit. Car, not cart. There we go. They're actually starting at 11 a.m. So before we get into specifics, they didn't tell us how long they've been on the road, but we do know, or we have an idea just by times, that one car has been on the road longer than the other. And if you guys want to guess, who is it? If you said first car, you were right. Started at 10 a.m., it's been driving longer. So just kind of keep in mind, this car has been on the road longer. And I'm writing it down to remind myself. So when I try to set up their times, I know it's going to have a bigger time. Or sometimes bigger, we say longer. The other concept I want to ask myself is, how much longer has this car been on the road? So if the car started at 10 and the second car started at 11, there's an hour between it. So actually we're even more specific. Been on the road longer than the second car, it's 1 hour longer. So that's even better. We have more information. So a lot of times, they're not really being clear, but I can actually figure out the times. We don't have clear hours, but if I don't know how long the second car has been on the road, we can call this X. So X equals the time the second car has been on the road. been on road. And if you have like an actual time and your first car has been on the road 1 hour longer, then your first car time on the road should be x plus 1. So at least we have times at this point. Now, that's great, but they didn't give us any other information other than the how fast the cars were going. But this is useful to us. I don't know if you remember us talking for previous examples, but if you know you've been on the road for just an hour, and just kind of think proportionally here. So let's say, and I know you don't have to write this all out, but I just want you to think. If you have a rate of 60 miles per hour, how far have you gone after 1 hour? So miles per hour, 1 hour, you've gone 60 miles. And what about 2 hours? Well, you've gone 60 miles for the 1 hour and another 60 miles for an hour. So you've gone 60 times 2 miles. What about 3 hours? 60 miles for the first hour, 60 miles for the second hour, 60 miles for the third hour. We have 60 times 3 miles. And if we don't know how long, that's what we call X hours. Or in our case, what was it? X plus 1 hours. Think about the pattern. In all cases, you've been on the road, you're multiplying it by however many hours, so 60 miles for each hour. And if your hours happen to be X plus 1, you actually have your distance. 60 times X plus 1 miles. So right away, I can label this A now is actually 60 times X plus 1. It's a distance. We don't really know what it is and we're a little uncomfortable, but at least we kind of have a setup. And if you wanted to understand like, well, why are you multiplying? Well, I'm thinking proportional thinking, just kind of making up a pattern and seeing, what's the same all the way along, what's varying. But I also have an idea that maybe comes back from our past, is that our distance is equal to rate times time. And that's kind of what we're looking at this point. But sometimes if you're not really interested in memorizing formulas and you want to think about what's actually happening, I like pattern recognition as well. So we're almost there. The same sort of argument. If we're going 75 miles per hour in the second car, you can think about proportional thinking. After 1 hour, you've gone 75 miles. After 2 hours, you've gone 75 miles the first hour, 75 miles the second hour. That's 75 times 2 miles, whatever that happens to be. 3 hours, 75 times 3 miles, rate times time, right? And then if we're looking at this, it looks like we've gone X miles. It's the unknown. X hours, I should say. Then this is where we go into and say, wait a second, that is 75 all the way through. What is changing is the time. That's why we have the X for the number of miles in terms of the distance. So now we can replace this leg instead of B. And maybe I don't want to erase it, but I'll write it in. I should have 75 times X. So I have distances in both cases. And now I'm ready. I'm ready to incorporate this into my equation. So I'm going to take this. The A again is 60 times X plus 1. And remember, it's squared. The B is also squared. That is going to be 75X. And that should be equal to 600 squared. And I know I could have figured out what that was, but I just want to keep the consistency going here. So I'm going to take this off to the side. I need a little bit more room, so bear with me. Move this over a little more, a little more, a little more. There we go. A little higher for us. Okay. So now we've got ourselves an equation for which we can try to solve. So before I even, work on my x's, I just want to figure out, well, I've got these extra squares going on. I do have a product being squared. What I might look at if I'm trying to understand this, I really have 60 times x plus 1 getting multiplied by 60. Well, I was trying to color code it for you. 60 times x plus 1. And then I also have 75x times 75x. I'm just writing this out so that we can really interpret this. Sometimes you have shortcuts and you can definitely simplify. What is 600 square? 600 times 600, just in case. Sometimes if you really just know what exponents mean, you don't have to memorize all these fancy math shortcuts and formulas. So what's nicer for me is the right-hand side of the equation. 600 times 600, I will use my calculator to find out that that is 36 with 4 zeros. 1, 2, 3, 4. So if I said that out loud, that would be 360,000. Gotta be careful. Now I can use my calculator also to, 75x times 75x, 75 times 75, that's 5,625. X times x is x squared. So that's nice. Now, if I'm dealing with this other part, this is kind of the trickier one, a little algebra for you. We can multiply 60 times 60. And I believe if you do 60 times 60, that should give you 3,600. But at least we have that part. But when you multiply x plus 1 times x plus 1, you actually have to use some of your past math tricks by trying to understand how do you FOIL it out, how do you distribute it. So we'll do that. That gives us x squared plus 1x plus another 1x plus 1. Keeping in mind that this 3,600 is still on the outside. We have to distribute it later. Simplify a little bit more, 3,600, still there. I have x squared plus 2x plus 1. Now equal to 5,620, not equal to, plus 5,625 x squared equals 360,000. So clean it up a little bit more. What we like, distribute the 3,600. So I have 3,600 x squared plus, what do you have, 3,600 times 2, if you need to, use a calculator. That's 7,200x plus 3,600 plus 5,625 x squared equals 360,000. If you need to, you can put a comma to remind yourself. I'll combine like terms. Looks like the x squared terms. So I'll use my calculator, 3,600. I mean, I'm already working so hard with the algebra, might as well simplify my life a little bit. 5,625 plus 3,600 gives me 9,225 x squared plus 7,200x plus 3,600 equals 360,000. And at this stage, you're starting to recognize what's happening. This, my friends, is a quadratic equation. And totally up to you how you want to proceed with solving. If you're on a roll with the analytic techniques, you might notice that you're like, well, might as well move everything to one side by moving the 360,000 over, being really careful about all the zeros. So you could try this and see where that leads you. 9,225x squared plus 7,200x. Now I have to be careful with all the zeros. 3,600 minus 360,000. So that's going to give me a negative 356,400. Now equals 0. So how you want to approach it at this point, I mean, the numbers are really huge, and that's realistic of a real life type of problem. You could definitely pull out the quadratic formula if you were interested. And sometimes that might be less frustrating than finding an appropriate window. But what it's really asking you to do is it's really asking you to find these solutions. And just a little bit of experience that I have with this type of parabola, I know that the x squared term is positive, so I do know that it's opening upwards. I'd be interested basically in figuring out what were the roots, what are the solutions, and if I could have my calculator to do this, it might be a little faster. You know, and it's kind of like a sacrifice on either part of, you know, whether you choose to continue analytically or whether you choose to use your calculator. There are pros and cons to each. But because we are a calculator class, I'll enter this into the TI and see what we come up with. So the big key here is remembering what I typed in. So I'm going to switch back and forth, but you'll probably just hear me talking to myself, which is what we do usually in math class anyways. So I'm going to go back to my TI. I have my old problem up there. I'll go to my function editor. And what I'm going to do is look at reminding myself, what did I actually have? So I have 9,225x squared. So 9,225x squared plus 7,200x. 7200x, just keeping care that I don't punch in too many zeros, and minus, and this should be 356,400. 356,400. I press enter. Now, just the idea of how this graph is going to go, you know, having a y-intercept of negative 356,400 right away tells me there's going to be some pretty big numbers in my window. So whether you want to press zoom fit or you want to adjust the window yourself, it's totally up to you. I'm going to take a gamble and try to adjust the window myself, but feel free to play. If I know it's a parabola that's facing upward, I don't really have to see the entire parabola. I just have to see where it crosses the x-axis. But maybe I'll kind of use that 356,400 as a starting point. So I'm going to go crazy and say 500,000 all the way around. We'll see if this leads me to a horrible dead end, but you know, you got to try. Sometimes things work, sometimes they don't. So I'm going 500,000. I think the X max, I think I'm exaggerating, but we shall see. I just want to show you that, you know, I don't always know where to start. So I'm kind of just using the y-intercept as kind of a jumping point. 500,000, so at least I have a square window. And, you know, let's see where this leads us. Let's graph it, see what happens. And it gave us a really ugly graph. Well, we see a line. I do see that there's a y-intercept there, so maybe I did go a little overboard on my x-min and my x-max. Let's shrink that down again. You know, maybe I should just stick with negative 5,000. Maybe that might be a little bit more realistic. Let's see, try that. Oh, I'm still a little overboard. Okay, keep going. Let's cut it down further. Negative 1,000. I mean, they asked me how long it'll take them to get 600 miles apart, so maybe that's a little rough. That's a lot of hours to be on the road anyways. So that would be unrealistic. So maybe I should be shrinking my hours down a bit. sometimes you forget that these problems are associated with real life situations. So by me choosing 500,000 hours on the road, oh my goodness, they should not be driving at that point. But anyways, I digress. It looks like let's shrink these hours down a bit more. Let's just go with I'll say negative 500 and 500 just because. Oops. And now you're starting to see that parabola form. It looks like it was really squished. So let me go even lower. Let's do negative 100. See how it's a little nicer to, how do you say, go from big to smaller, because then you can kind of adjust along the way. And then now you see your zeros. So, I mean, you can leave it there because your graph can probably find it. But if you really are like me and you want something prettier, you may even go further and just go negative 50 to positive 50. And there we go. That's a really beautiful parabola. So what you'll do, you can calculate your zeros at this point. So see what I mean? You know, would it have taken us longer to use the quadratic formula and simplify things down? Or would it take us long to find a window? You know, we don't know. Might have taken exactly the same amount of time. So I've got one of the zeros. I shall write this down so I don't forget it. So I have negative 6 point, I'll say 62. And then the other zero. I'm going to go to the other one. And that should give us about 5.884. And so let's copy. Let's see if we can copy. We'll go back to our work. See if it'll let me. Nope, I guess not. Okay. I'll do a quick sketch. And actually, we had started off with a quick sketch. Looks like we somewhat have something. So we figured out that one of the zeros was 5.84. The other zero was negative 6.62 about. Now keep in mind what X stands for. X stands for the time the second car has been on the road. So when you talk about time, can you have negative time on the road? And you're thinking, no, that wouldn't make sense. So remember how these are all associated with real life situations. So that first zero, I shouldn't have even wasted my time on it. But I always like to do this to kind of help you guys see that sometimes we don't know or we forget. We're so involved in the problem. So it looks like we do have X equaling 5.84 about hours. So we just want to make sure what we're trying to understand. X is the time the second car has been on the road. So if you're trying to answer this question, when they say how long will it take for the cars to be 600 miles apart, we would choose that X value. We would not add 1 to it because really the hour or the time didn't really start until that second car started. So I guess if you're doing clock time, you'd base it off of the second car anyways. So we can now finalize our answer, you know, if we want to take the mathematics. Therefore, it would take about 5.84 hours for the cars to be 600 miles apart. And that's again where you make the big bucks, when you can say things in English after you did all that complicated math. So that was super, super fun. I'm sure you enjoyed yourself. Really good exercise for your brain, just thinking through all these things. And even though you might be feeling a little bit strugglesome in this sort of idea, you know, the more you struggle here, the better off you are for the exam because you're exercising your brain. So I hope this helps. I will see you in the next section.